Hello, everyone. Good morning, good afternoon, and good evening, wherever you are watching from. And welcome to day 2. Today, we will take a look at, or we'll introduce ourselves to Pyproj, which is the Python library for cartographic projections and coordinate transformations. So let us take a look at our agenda for today. Today's outline, sorry about the banner, I should have changed it. Sorry. But we are not doing Fiona and Shapley. I think I've changed it in the other slides. I forgot to do it for this one. So we will introduce ourselves to cartographic projections and then what coordinate reference systems are. We will also look at introduction to Pyproj, which is Python's a Python package for doing such things. So what is a cartographic projection? It is a technique for representing the three-dimensional curved surface of the Earth on a two-dimensional flat plane. So think of it like how we kind of transform the world we see onto a plane which is flat, where we can do mathematical computations with ease. Because given the shape of the Earth and the curvature and how it is not uniform, we cannot really perform mathematical operations easily. The Earth is a geoid, roughly spherical, and so if you attempt to do mathematical computations here, it will be very, very difficult. I don't think we have models to do that yet. Maybe they are there, I don't know, but those models should be very, very difficult. So we project them so that we can draw the Earth on a flat plane and do those calculations. What is the importance of such a thing in geospatial analysis? Well, the choice of projection affects your results in terms of distance or area or even spatial relationships. This one is kind of a trade-off, something for something. So depending on what you want to really preserve, if you want to preserve distance accurately, like to the best you can, then you choose a particular type of projection. If you want to represent area more accurately, you choose another type of projection. And so with shape and direction and all the rest. So understanding these distortions help you to choose the right projection based on your map's purpose. So a few examples of the projection is the Mercator projection. That one does well at preserving angles and shape, but it distorts size. It's especially around the polar region, the sizes of the countries and the countries there appear larger than they actually are because of how the Mercator projection works. And we have the Albers equal area projection. It will give you the correct area or to preserve your area to the best it can, but your shape will be distorted. And so that one is also useful for landmass comparisons and other stuff like continental maps. So if you see any map displaying continents where some of the, you see, no, this continent, it looks like the area, it's not that close to reality. Most likely they are using the Albers equal area projection. And then we also have the popular universal transverse Mercator, which divides the Earth into several zones. And that one is particularly useful for regional and local mapping. And it really gives you accurate distance if you choose the correct zone for your area. So now we move on to projections and transformations in Python. And as I said, Pyproj is our library that we'll be considering today for those kind of things. And some of the key concepts I want you to note before we move on to VS Code is, don't forget these two things, that there's one class called the CRS class, which defines a coordinate reference system, and the transformer class. Those are the two we'll be using the most today. So just get them somewhere and then we can move on. Okay, so I'll come to Visual Studio Code. But before I do that, the plan was to upload a video that shows how to solve that issue of the environment file not found when you are creating an environment in Conda. But the video is done. I'm yet to upload it. I couldn't upload it before this stream. So for those who are having problem with their environments and Fiona not working and all that, if you have a Google account, please open your drive like I have done here. I'm currently inside my drive, inside one folder called Collab Notebooks. I don't know whether you can create it anywhere, but I have this folder where I create my Collab Notebooks. When you are here, what I want you to do is to click this new button at the top, choose more, and as part of the options, you should see Google Collaboratory. So click on that one. It will create a Google Colab notebook for you. It is, think of it like a Jupyter in the cloud hosted by Google. We can install our stuff there. We don't need to really create an environment. You can install things and then just get started. Okay, so whilst this one, okay, is done. So once you create it, first thing you can give it a name here. So maybe I'll call this one day 2 because today is day 2. And then for those of you who will be using this Google Colab, what you have to do is to type exclamation mark and then pip install GeoPandas. Maybe intentionally install Fiona. I think the GeoPandas should bring it. Let's see if it brings it, then we leave it. If it doesn't, then we install them separately. So it is exclamation pip install GeoPandas. And then this place, you can choose to connect to a hosted runtime so that you get access to use Google's compute backend instead of your own resources on your computer. Let me go to the bigger screen. Okay, so this one, I click here to run it. And then I've been using it for other things. So you see that it has other some of those even already satisfied for me. So it installs this inside my Google Cloud somewhere. So you see that I have Shapely here. I don't think there is Fiona. So what I'll do is that I'll add Fiona to the list like this. And there's Pyproj, so we shouldn't worry about that. And I'll run this particular line again. Okay, so I know that it's completed successfully. I have my green check mark at the bottom here. So what I can do is to create a new cell. Will this collapse the code? Hide output. So I've hidden that output. And then I'll click this plus here. I think when I hover, it should come for me to create a new code cell. Here I can say import Fiona. And then maybe I can import Shapely also. And then I can also import the other library we are using today, Pyproj. And then what I can do to try them is to just run this code. If I run it and no error happens, I'm one step closer to the solution. But one of the things that we can do to also verify the installation properly is to say, okay, that's what I was about to type. The AI got me there. So I'll accept this one from the AI. So just Fiona dot underscore underscore version underscore underscore. If you print this one out and you receive the numbers properly, then it means they are properly installed. And then you can continue today's tutorial. You just type whatever you see me type in VS Code, and yours will also work for you. Okay, so that was just by the way to show those who have problem with their environments. But I will go back to Visual Studio Code, and then we will take it from there. Okay. So that is my Visual Studio Code. I'll close this one. You don't need it. And then I will create a folder called day2. So I'll create that one inside this parent folder. So I just make sure that I unselect the day1 folder, maybe click outside. Just make sure that you have this big blue box showing. And then you can create day2. Inside day2, I'll create my file. Maybe this one, I'll name it properly, day2.ipynb. And I'll press enter. Okay, so I'll go ahead and select my kernel here, which should be Geospatial. And then today we are looking at Pyproj. We saw an introduction to the coordinate reference systems. I think I also found some useful links that I will visit if need be. If not, I think I'll have to list them somewhere. Okay, so the easiest one we have to do now is to define a coordinate reference system. So I'll give my markdown, and this place I'll say define in CRS. And then add a code cell below. So what I have to do is say from Pyproj import CRS. From Pyproj import CRS, sorry, not this CRS, it's capital CRS. So import CRS. And then let me run that one for now. And then add a new code cell here. Let's say I want to define the global WGS84 CRS, so I can name it inside WGS84. And I set that one to be equal to CRS dots. There are many ways to create a CRS, as you can see from this place. We have one from authority, from CF, from dictionary, from EPSG, from JSON dictionary, Proj4 string, from user input and WKT, and all of them. But I will not be able to introduce you to all of them because you don't need all of them. You only need one. And then if you know how to use it, you can use it for whatever you want to do. So I'll use the from underscore EPSG. And what I have to pass in here is the EPSG code. So you can see here that it takes the code, which is an EPSG code. I'll tell you what the EPSG code is shortly. So I put 4326. So how did I know that I have to put 4326? Well, if we bring up our browser, and then we are done with this. Okay, I shouldn't have closed it. But if you come to this place inside Google and then you search for the name of the website, maybe you should search for it up here. Type epsg.io. It should take us to an official website for the European Geospatial, European Petroleum Survey Group. I think that is the name, the full name. Yes, yes, that should be the full name, something like that. I think the European Petroleum Survey Group, or maybe not. But if you come to this website, which is the official website of the EPSG, you can search for anything here. So you can search for any coordinate system in the world, either by the country or the code or the name of the coordinate system. So I typed in 4326. When I press enter, I will see that this 4326 corresponds to the World Geodetic System 1984. And I will see that the area of use is the world. So it's a world, everybody in the world can use WGS84. So that is how come I know it. And also because I've been using these codes a lot, I do a lot of geospatial analysis. So that was it. So if you are looking for any other code, so maybe you want to type in your country, you can type your country here. You see your country's coordinate system here, and then you can put that value, that EPSG value there instead of the 4326 I'm putting there. Okay, so with this, we have defined a coordinate reference system. If I run it now, nothing should happen because we are not telling it to do anything afterwards. But if I want to see it, I can just say WGS84. And when I hit run, I see some things displayed in my notebook here. I created it, I called it, and I see these things. And I see that it's a geographic 2D coordinate reference system with an EPSG code of 4326. And then the name here, the axis info, and then all of those other stuff that you should expect up to the prime meridian. This thing can be expanded. I think we will get to that place where we will see how to get data from EPSG. If today's time permits us, we will take a look at that one also. So if I also want to define a new coordinate system, I am in UTM zone 30. Let me put 31 north. So if I put that one in, I can say CRS dot from EPSG, and I put in the code for that. I already know it's offered. It's 32631. And so you can also, if you want to search, you can come in and search, but I don't think that should be necessary. But if I come in and say UTM 31N and I run it again, I should see the details of that coordinate reference system also. So the meridian is Greenwich and all that. Okay. So that is it about creating a coordinate reference system inside of Python using Pyproj. And there are other ways to initialize it. As I said, if you want to initialize it from the EPSG string, you can put string here. The other part was from string. And in that case, instead of just putting the number there, what I have to put there is inside a pair of quotes, I put EPSG colon, then I put the code there, 32631. And when I run it, I should get the same output. But I don't prefer this long method. I can just put the number in here instead of just typing this long string. So that is it about initializing a coordinate reference system or defining a coordinate reference system. The next one is how we can view the details of a coordinate reference system. So there should be a way for me to collapse this. Okay. So viewing the details of a coordinate reference system. Viewing CRS details. There are many ways I can do that. And I'll be using this particular one we have defined already in memory. If I say, for instance, UTM 31N dot to EPSG, if I call this method on it and run, it will give me the EPSG code of that particular CRS. And if I also say dot to authority, and I run it, it will give me the authority, which is EPSG, and as the code itself also. Okay, and if I also want to see the CRS, well, what I can do is I can choose print, and then inside here, what I can do is to call the CRS I have defined, and then call the dots to WKT. Now, this WKT, I think we have to look online for it. It's a well-known text. This is one of the ways of, let's come up to Google and search in here for WKT. You see it's here for well-known text representation of a geometry. So let's, oh, okay, I think this is their website maybe. instead of the Wikipedia. Okay, Wikipedia open first. So this is well-known text. I'm looking for an example. Okay, so I want examples with coordinate reference system inside. Looks like I can't really find what I'm looking for, but that is the name. That is the name there. So let me open. I think this should be the WKT website. Okay, so it is also just like that. Yeah, but you can read more on it if you want to. So it looks like that is what Shapely has even been using. You can read more on that one. So when we printed the WKT string, well-known text, this is what it gave us. Well, it looks like everything is on one line. So if you want to see this nicely, you can say pretty. I think the command is pretty. No, not that one. Pretty equal to true. That means that you want Python to prettify the output for you. Oh, it's saying that it doesn't know pretty. Okay, it should be inside this WKT. It's not outside. So I can just put here pretty equal to true. So we don't pass it to the print function. We pass it to the WKT. So this one has, instead of one line, it has broken it down for us. And this, if you want to see details of a particular coordinate reference system, you have to use this method instead of just calling the CRS like I did in line 3 here. Because you see this one, it gives you into details the ellipsoid. I think this should be the semi-major axis and semi-minor axis. One of those, some of those parameters are all here. And you see the units even in meters, and then latitude of natural origin. And then all of those other ones that you will expect a coordinate reference system to have, it gives you all of those things in detail. And it's even saying that the output is truncated. That means there is more. So I can view it as a scrollable element, and that should give me all the rest that is hidden. Okay, so that is also one of the ways to visualize the coordinate reference system. There are others on Pyproj's website. You can check them out if you want to. So let me just search for Pyproj docs. Don't need this one. I don't need this one also. So if I go to the Pyproj documentation, and I think I should come to maybe getting started, should have something like that. So you see here, this is the place where it is going to authority. And I think this is, so this is an example of the proj4 string, if you care to use it. And I think this is the place where it's also printing like we did. And there are other options down here for you to visualize. I think this particular one also, where you import the WTK version from the enums of, from the enums of, sorry, of Pyproj, and then you can visualize it also in this manner as well. Okay. I don't think we should have closed it, but no problem. Okay. So now that we have seen how to create and even visualize those ones, let us move on to how we can perform a coordinate transformation. So I'll scroll up again, double click on the left side. That should collapse the output for me. And then here I'll give my markdown that says performing a coordinate transformation. Okay, so I drew your attention to two very important classes, one which was CRS, and now we're about to use the other one, which is the transformer. So we have to import the transformer from Pyproj. So we say from Pyproj, we want to import transformer. Think of the transformer. The transformer is what helps us to do the transformation. So before we can perform a transformation, we have to first define the transformer. And how we do that is to say maybe transformer. You can give any name to this variable, but I just like to follow convention and make my code readable. How you create a transformer to say transformer dot, and then maybe from, sorry, not from, and then CRS. You see, you can create it from Proj or pipeline, but CRS is the easiest. And then here we pass in the particular coordinate reference system that we want to use. So let's just pass in the popular WGS84 geographic. So what is 4326? And then in here, you pass in the code for the coordinates you are transforming from, and then you bring a comma, you add the coordinates, the code for the system you are transforming to. So let me take 326, should it be 30? That means I'm converting from WGS 1984 to this code, which is for the code up there should be for WGS 84 UTM zone 30 north. That is it has a code of 32630. So I'm projecting from, I'm transforming from WGS Geodesic World Geographic System 1984, the geographic coordinate system, to a projected coordinate system, which is UTM zone 30 north. Okay, so what I want to do is for us to verify that what we are doing actually works. I'll come to the EPSG website. They have a map here, so let's open the map. And then I'll look for a place. Let me close this ad. A very popular lake in the world, Lake Bosomtwi, which is believed was created by a meteorite impact many years ago. It should be somewhere around this place. These people should, where would this thing go? How do I get rid of this one? Okay, just manage for now. I don't know why that ad is there and it doesn't want to go. But I'm looking for this particular lake here. And once I make sure that my crosshairs are on it, you see that it gives me the coordinate up here. But because I want to also verify with Google Maps that the transformation worked, I'll change this to 32630 here. And then select this one rather, so that I get the coordinates in UTM zone 30. So I'll copy this, or maybe the two of them together. Okay, I can't copy two, so I just have to copy one of them. Okay, things are running a bit slow here. Forgive me for that. So I come back inside my project, and maybe I can say from. Okay, from is a reserved keyword, so maybe points from, points underscore from, and I can set that to, let's make it a tuple. I paste the X. let me go and get the y also. And so I can bring that one to in. And then paste that one to in. Okay, so now because I'm reversing it, I have to now put 32630 and then the 4326 here. The reason I'm doing this is that I want it to give me the geographic coordinates so that I can test those coordinates in Google Maps to see if they fall at the same place. So now that I have this transformer set up, what I can do is that I can now do the transformation. So transform. And then here, it will give me two items, X and Y. So I can immediately access all of them and say that X comma Y, and then set that equal to transformer dot transform. And what do I want to transform? I want to transform this point here. So I can pass in points from. And then if I tell it to maybe print X comma Y, if we have done everything correctly, when I run this code, okay, so okay, I have an error here. It says transform missing required positional arguments YY. Okay, so it's taking all of this to be X. I was thinking because it's a tuple, it will just spread it. Okay. So what we can do is to say points 0 and then another points from. Forgive me for those pop-ups. And so we access the first and second element. And then now it gives me this coordinate that this is the WGS equivalent of the lake I just copied. So what I can do is to come inside here and we want to test this library and see. And so I'll go to maps.google.com. And then one of the things I can do to search for any place here is if I have the coordinates like this, I can paste it in. And then I think I have to put a comma in between. And then when I hit enter, let me come down small. When I hit enter, you see that it's taking me, this is the point that's taking me to this blue lake, which is the lake Bosomtwe itself. Let me hit enter again. You see that it will load and take me here. So we know that transformation was successful because we gave it UTM coordinates and it has given us geographic coordinates. And so that is how we perform transformations inside Python with Pyproj. So you just have to get the EPSG code for where you want to convert from and to. I've shown you where to get the code. Even if you don't know this code, just type the country where that particular points fall, and then where the country where the other point is supposed to also fall. If you also know the name, just the name of the projection in mind, maybe UTM zone 30 or something like that, just type it in there and it will give you the code for you to feed the transformer with it. Okay, so that one too is it for the coordinate transformation in Python. The next on our list is to learn how to do some projection. Yesterday we looked at Shapely, so we'll see how we can project Shapely points or Shapely geometries into or with Pyproj. Sorry. For that one, let me also bring a mark down here. And then maybe say projecting with Shapely and the Pyproj. Scroll down a bit and then bring in my code. So I will just project a single point. You can try it at your end with the line string and the polygon. Just one example should suffice. So from shapely dot geometry, we want to import here our point object, and then we have already imported a transformer up there, so we don't need to import it again. I usually like to keep imports in separate cells, so I'll not add the code here. I'll come to a new line. So my point here will be, let me put this one as the point to see if it will give me back the same coordinates here. So this point will be point, and then I'll pass these two in. And here I will have to bring a comma. And so what I want to now do is the reverse of what we just did at the top there. So maybe I'll create a new transformer. It will override the other one in memory, but that is completely fine. That should be equal to transformer dot from CRS. And this time around is the reverse. So I am rather going from 4326 to 32630. And then, the default stuff, I have to now come and say, maybe UTM point, that should be equal to transformer dot transform. And then here I can say point dot x, that should give me the x part, and then point dot y. This one we are not assessing it like we assessed the tuple from here, because it's a point object, and when we call the dot x on the point, it will give us the x part. When we call the dot y, it will give us the y part. So what I can do is to now print, and maybe in an, okay, I just print the UTM point and see what will happen. Not this one, UTM point. So let me run the code. And then this is the value it gave me. So let me copy it, come up here and try the comparison. Okay, it is the same, exactly the same, even in terms of the decimal places. So that is quite impressive. So that is also how we can transform shapely objects from one coordinate system to the other. Okay, so the next one on our list will be there's a way we can even define our own coordinate reference system. So let's look at that one, how we can define our own coordinate reference system. Sometimes if you go to certain industries, I think like the mine, they have their own system that they use, so that even if an adversary gets access to classified data which has location, they will not really know the position of their staff like that. So yes, so sometimes it depends on so many things. You may need a coordinate reference system, a custom one, and Pyproj allows you to create one. So let's see, defining a custom CRS. For that one, let's start with a geographic one first. So maybe a geographic CRS. We have to import the geographic CRS from Pyproj. So that'll be from pyproj.crs import geographic CRS. And all that we have to do, maybe you call it GeoCRS. All that we have to do is to say geographic CRS. Even if you don't pass in anything now, it is defined. Because if you look at, we can pass in a name, a particular name. Let me pass in the name here as maybe say my fantastic CRS. And other things that we can also pass in is the datum. You see here that when I hover over it, I will get some of the, we call this one a documentation. The name of the CRS, the default is undefined. And then you also have to pass in a datum. That one is required. But here we see optional because there is a default. So we can accept, we can pass anything that this particular manager accepts, or if we also create our custom datum, we can pass that one to in. And then this ellipsoidal coordinate system also, usually, I think there was one thing I didn't show, but if I come up here, I think it's not too late. I want a geographic coordinate system. Like this WGS 84 here. If I say dot, I think there's a way to get the ellipsoidal. Is that a geographic? Let me see. So if I have a projected coordinate system, a coordinate reference system, and I want to get it geodetic, I think I just call the geodetic on it, and you see that it's giving me the geodetic or coordinate system that corresponds to this UTM. This UTM is projected, but I want to get a geographic coordinate system that corresponds to it, or that the UTM depends on. And once I call the dot geodetic CRS on a projected CRS, it will give me that information there also. So if we come down here, you can also specify, because we are now creating a projected one, we can define the ellipsoidal CS of it. But if we were creating a geographic coordinate reference system, sorry, a projected coordinate reference system, we would have the option also to define the geodetic part of it. But we will not define all these ones. We will leave the default for this one. That is the, no, the default is, I don't really know this EPSG code of 6326. Let me find out. So I come back to epsg.io. The 6326. Which one is that? Oh, I got it wrong. It's 6326. Okay, I don't really know why it is not getting it, but let's leave. I think it should still be able to get. I don't understand why it's not getting it. This should get it. Okay, my browser is running slow. I don't know why. I think there was just an update before I started the stream, and it is causing it to run slow. Okay. Well, this should be some response from some particular API. I don't know why it is not showing, but not like it is non-existent. That this coordinate reference system should be there. So I think it has datums here. Close. Okay. Sorry, my bad. I should have clicked on the datum because it gave me more than one result. So I should have clicked on the datum. My bad. And so this particular one that is the default is the World Geodetic System 1984 ensemble. So we can leave that one as default, or if we want our CRS to be based on another thing apart from that one, we can just copy the string here and then come in and say datum set the datum equal to one string. And then once we know our EPSG code, I'll bring them on separate lines. We know our EPSG code that we want it to base on. We can change it here, maybe to 4326. And then that is it. We have created a geographic coordinate reference system, a custom one. Okay. During handling of the above exception, something occurred. Invalid datum string. Okay, so I was just trying to be a little bit smart with Python or Pyproj, and it caught me right there. So since I don't know the particular string, I think I'll have to search the Pyproj website for the specific strings for each of these coordinate systems, the geographic ones. It might be different than what I'm thinking. So if I run this one now, I'll not get an error. So if I want to see the details of this CRS too, I can just say GeoCRS. And then you see that the name here is what I give it, my fantastic CRS, and other stuff also. But surprisingly, this one is calling the WGS84. Okay, so that is it. If you want to create your custom geographic CRS, it's something like this. And I think there are other things that you can add in here. But in most cases, you may not even need to do this. So if you also want to create a custom projected coordinate reference system, which in most cases, if you are creating a custom coordinate reference system, it will not really be a geographic one. It will be a projected one. So let us look at how we can create that one also. So I'll put that one in a new code cell and call custom projected CRS. That one is a bit different from the geographic. So we can now say that from Pyproj, not PyCompile, Pyproj.crs, we want to import. We import geographic CRS. We will also import projected CRS. Let me scroll up so that you can see the text. And then we also need to perform import the UTM conversion also. So from pyproj.crs.coordinate, I think it's coordinate operation, coordinate underscore operation. We want to, okay, it's not underscore CRS, it's just the CRS. From this, we want to import UTM conversion. And then the last import we have to do is say from pyproj.crs, not this one, crs.datum. We also need to get the datum, so we can either import a custom datum if you want to create a custom datum, and also a custom ellipsoid, because we need a datum and the ellipsoid to create the projected coordinate system. So let's define our ellipsoid. Ellipsoid first. So ellipsoid. And then that one will be a custom ellipsoid because we are creating our own ellipsoid. In here, there are things we have to pass in, like the semi-major axis, the semi-minor axis. And then if you also have the inverse flattening, you can pass it in the other stuff, but you keep it very simple. So you can pass in the radius also, you can pass in the inverse flattening, but we will only pass in the name and then the semi-major and semi-minor axis. So let me bring them on separate lines. So for the name, I can say my fantastic ellipsoid, just to tell you that you can put any name you want there. And then the semi-major axis, we can, if you are creating a custom CRS, projected CRS, then it means you have already worked out and you have all of these figures there. So I'll use a random number here, maybe not random, I got it from the internet, so it might as well belong to one of the ellipsoids. But for your own case, if you are creating it, then you should have all those things in place before. So 63781 and then 37. And then my semi-minor axis should be, this thing should go away, should be 6, 3, 5, and then 6, 7, 5, 2. Okay, so now our ellipsoid is created. I said there are other things we can pass, but we are only sticking to this 3. And then the next one that we can create, I think this one can all go on one line. Oh, let me I just reduce the size a bit. I hope you can see it. I just want to keep things simplified so that you don't have to scroll up and down. Okay, still not even occupying. So I'll leave it like that. And then the next one we create is our datum. And then that one will be a custom datum. And then in here, we have to pass in the ellipsoid. So the particular ellipsoid of the datum is our custom ellipsoid that we have created, not ellipsis, ellipsoid. Or maybe you should give it a proper name like custom ellipsoid. So that means that this place we have to call the custom ellipsoid. And then after we pass in the ellipsoid, the next thing that we have to pass, you can see it takes the name ellipsoid and then a prime meridian. That should tell it where it starts from, where it starts the divisions from and all that. So maybe I should give a name like I've been doing. So in this place, I'll call it My Fantastic Datum. So in your case, you have a name for it. So just put that proper name there. And then the prime meridian, I can choose maybe Greenwich or maybe Lisbon. It can be anything. So there's the meridian where your particular projected, your particular custom CRS should pass. I think you should put that one there. And then now we have everything we need to define our projected coordinate reference system. So I'll say Proj, short for projected CRS. That should be equal to projected CRS. And then in here, I pass in my conversion. And then I pass in here UTM conversion. And then you see inside this UTM conversion, I'll have to pass in the particular UTM zone where my projected coordinate reference system, the custom one I'm defining, will pass. So you have to know that one too before you define a custom projected coordinate system. I think for the Greenwich should be, shouldn't the Greenwich be 1? Because that is the line 0. So let me just put it in. I'm hoping that will not throw an error. And then here I have to also pass in the geodetic CRS. And then I will create one on the fly. So let me bring this one on the next line, like I've been doing. So for this geodetic CRS, remember we imported it at the top here. So I can say geographic CRS. And then this one requires the datum. So I can pass in that the datum equal to, let me name this one to custom datum. Custom datum. So the datum is custom datum. So once I do it this way, I have created my custom projected coordinate system. So what I can do is to call it, so I can say Proj CRS, crossing fingers that everything was done properly. And yes, I did everything properly. And so that gives me my custom projected coordinate system. So if you are working in any industry that requires you to use a custom coordinate reference system, most likely to be projected, because I'm really thinking through why you should create a custom geodetic coordinate reference system or geographic coordinate reference system, usually to be projected. So this is the step you go through. You just make sure that you have the parameters for the ellipsoid, and you can give it the name properly, and then you have the parameters for the datum, also knowing where your prime meridian or the particular meridian that passes there. You can do searches online, you find that one. And then the UTM conversion, also make sure that you pass in the proper UTM zone. And this place I should have given a name as always to be my fantastic projected CRS. And don't forget this comma. So if I run it again, now it will not tell me that the name is undefined, is my custom, my projected CRS. And then all of these things are in here also. So that is also how we can create a custom CRS in Python. Okay, so if you want to read further on map projections, I think I have a couple of links here we can visit. One from Axis Maps. So let's get back to Chrome and see what we can do there. So I'll link all of them in the video description when I upload them, so don't worry. This one is from Axis Maps. And I think I got one also from MetaTech. Let me open that one too. And I got some good information also from one Wikipedia page. So I'll open that one too here. So this is from the Axis Maps. And so they explain certain things here. You can go through the site and then familiarize yourself with it. I found something very interesting here. They seem to have some nice quotes and inspirations for the things they write here. And I took a particular interest in this one. That says, do nothing perfect, but most things well enough. So you should target perfection in all that you do, but if you cannot do something perfectly, at least try and do it well enough. And I really like this quote. It made my day. And so you can go ahead and read it, and it tells you how and when to choose a projection and all that. So as I said, the link will be in the video's description. You can visit the site. And these people also, they didn't have a quote, but they kind of explain the projection types to you. I don't understand this language, so I'm not clicking accept. So you can go through this one, and then there are some other related posts also if you find them interesting. And then the Wikipedia page, which goes into detail into most of the projections that we have. So you can see the type, the properties, and all that. So you can go through if you want to read further on some of these things. Other than that, you don't have to go through, and you probably already know how to do so. That is fine. So that is not all there is about Pyproj. In fact, if you should go back to Pyproj, this is the documentation page. There are a lot of things you can do, a lot. But the basic form is the cartographic projections and transformation, which we have looked at, how to create even our custom projections, how to define a projection, how to do coordinate transformation. We have looked at that one also. But if you come to the getting started, there are a lot of things here that you can take a look at. I think one of them, when I was going through their documentation, caught my attention. We will see if that one works. Okay, so you can even perform geodesic calculations here. Remember yesterday I told you that the distance that Shapley gives us is Euclidean distance, and it doesn't work well for geographic coordinate systems. If you are using a geographic coordinate system, what you want to calculate is the geodesic distance. So there's an example here. Maybe we can just copy then paste it. Okay, this one is not calculating the line length. Okay, I think this one is very, very simple and straightforward. So I can copy this code. And then when I paste it, don't worry, I'll explain it to you. Okay, so let me create a new code cell here and then paste what I copied from their website. This should be redundant. So they have this geod class. Let's move over it and see what it does. It performs forward and inverse geodetic or grid circle computations. So that is what they use to perform their geodetic computations. The forward computation using the forward method and blah, blah, blah. So because we are performing a geodetic computation, one that takes into consideration the curvature of the earth, we have to use this particular class. And this one you're already familiar with, which is the point and line string from Shapely. And then this line is defining a line string. The line is defining a line string. Wow. Okay. The line of code is defining a line string. And then this one is creating the geod object. So we are able to perform the calculation. And it is stating here specifically that I want to use the WGS84. So there are other ones. So if you want other ones, you can put them here. And then the total length here is the geometry.length and then the line string. So it is more or less like computing the distance between this point 1 and then point 2, just like that. So if we run it, we should see the length properly given. So if we should test, let me quickly compute the distance also for this one using Shapely. And then let's see. So I can say distance Shapely, that one equal to, let me paste them and then do some lazy coding here. So I can say 0.1 dot distance. I can call the distance on it straightforward and then pass in the 0.2. So if I print out distance Shapely, let's see the difference that will come between the two. Okay. Okay, this one is not being printed. That is why. So print and then paste this one. When I run this, you see the difference between the two. So if you want to perform geodetic calculations in distances, if by all means you cannot project your coordinates from geographic to projected, and by all means you have to use the geographic coordinates, and you still have to compute a distance. Please don't call the dot distance object directly on your coordinates. Convert it to this geod, and it will know how to calculate the distance for you accurately. Okay, so let's get back to the website and see if there's other things we can look at. So in the same way, there's geodesic area. This one, I think, is just defining the latitude and longitude. So they'll be mapping this one to this, and this to this, and all that to form the area. And there's also the geodesic parameter. Also, so you can go through these examples if you find them useful and convenient to what you are doing. Okay, so I will, as always, leave some 1 minute for questions and check if there are any. Other than that, it has been another wonderful day, and we'll say goodbye to today and anticipate for tomorrow. Okay, so there are no questions. Thank you very much for your time. Today also, the stream will be uploaded as always, and I'll try and do that immediately afterwards, together with the one that will show you how to fix the environment error. So have a nice day, all of you who are still in the day, and have a good night, those of you who have to retire to bed. And make sure you keep on practicing and practicing. That is the only way that you get to know and understand how these things work. Until next time, it is goodbye.